Hello everyone. I welcome you all for this interaction session, which is the fifth interaction session for the course Atomic and Molecular Physics, which is being flowed by NPTEL this January 2024 session with course code NOC24PH04. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So today we will be solving a few problems which is based on the week 5 lectures. It will cover the spin orbit interactions and hyperfine spectra along with some questions related to G-man effect and other multi-lepton atoms. So let's start with the first question of the day. So now this question says the line of X-rays emitted from an atom with principal quantum number n equals to 1, 2, 3 arises from the transition of option A n equal to 4 to n equal to 3, option B n equal to 4 to n equal to 2, option C n equal to 3 to n equal to 2, and option D n equal to 3 to n equal to 1. So these are the options. So I will give you a few minutes to try. Then after sometimes I will do this. So this is basically this question is based on X-ray spectra. I will discuss a bit detailed about the different levels and the transitions, and we will find out which transition corresponds to L beta line of the X-rays. So we will discuss the question one. Now, if you see, this question is based on the fine structure of X-ray emission spectra. So basically, this fine structure, the explanation is given by Cosels. So this Cosell's explanation of X-ray is in terms of electronic transitions in different levels like K, L, M and other levels. So we will find that since the transition occurring from any higher level to K, L or M, like all these levels. So since there are other levels also, so the components are found to be not single lines. There are some multiple lines. Each series consists of some number of components, and these components, suppose something is occurring from higher energy orbit to n equals to 1, that is KSL, then the lines are called as K alpha, K beta, and again this K alpha, K beta are again divided into K alpha 1, K beta 1, K alpha 2, K beta 2, like this. So how we will determine which transition corresponds to L beta line? So what we will do? Now let's consider different energy levels and then different end states. So if you make a table, if you see Suppose this is K cell, then for K cell, n will be 1, then n will be 1 means multiplicity 1, and this is nothing but 2s half. Here 1 is n. Then for K L, for L cell n is 2. So for L cell it has three components. Then it has three multiplicity is 3. So these three are nothing but L1, L2, L3. What are they? They are 2. 2 is for n is 2. 2s half, then 2p half, and 2p 3 by 2. So 2 will be lying here because your 2 is n. So these are the number of levels. Similarly, for K, L, then M. For M, N is 3. Then the multiplicity is 5. So M1, M2, M3, M4, and M5. So like this. So if you arrange the all these things in terms of energy levels, so how it will be appearing? So it will be somewhat like this. So if you see K, we just discussed K has only one level. So this is a single level. Then after that, L has three levels. Then M has five levels. Then K, L, M, then N. N similarly will be having seven levels. So this is 1, 2, 3, 4, 5, 6, 7. So this is K, this is L, this is M, and this is N. Here, if you consider N, N is 1 here, N is 2 here, N is 3 here, N is 4 here. So what are those levels? It is 2s half, then this one will be 2s half, 2p half, 2p 3 by 2, 2s half, 2p half, 2p 3 by 2, 2d 3 by 2, 2d 5 by 2. Similarly, considering about these seven levels, it will be having 2s half, 2p half, 2p 3 by 2, 2d 3 by 2, 2d 5 by 2, then 2f 5 by 2, 2f 7 by 2. So these are the levels, and we will now do the transitions. Now what are the rule for the transitions? So basically this is optical spectra because X-rays are nothing but the optical radiations corresponding to electromagnetic radiation. So for it the selection rules are delta n will be arbitrary because that is the transition can occur from M to K, L to K, N to K, and then other options, other selection rules are delta L is plus minus 1 because there will be change in the L value because there are mostly electric dipole transitions. Then delta J will be 0 plus minus 1. So if you draw the transitions, then you see delta L is plus minus 1. So if you're considering the transition from 2 to 1, then S half, 2S half to 2S half is not allowed. So the allowed ones are 2p half to 2s half, then 2p 3 by 2 to 2s 3 by 2. So all those transitions which are occurring from any arbitrary to the k level, these are called as k series. So similarly, these are the transitions. So these are called as k series. But if you see, there are more than one number of components. So since the transition is occurring from L to K, that is n equal to 2 to n equal to 1, then these transitions are called as k alpha lines. So these two are collectively called as K alpha lines. Again, these K alpha lines are classified into two. Since there are two lines, one is K alpha 1, another is K alpha 2. So the alpha 1 is the transition from 2p half to 2s half. So this one is K alpha 1 and this one is K alpha 2. Like that, if the transition is occurring from M to K, then there will be how many transitions? Then there will be two transitions, because if you see the, the delta L is plus minus 1 and delta L is 0 plus minus 1. So the transition will be occurring from 2p 3 by 2 to 2s half and 2d 3 by 2 to 2s half. So if you see, the two transitions will be again 2p half to 2p 3 by 2. So this will be from here, then other transition will be from here. Because here both are p and each is a, so delta L is always plus minus 1. So no transitions will be occurring from D levels, because for D L is equal to 2 and for S L equal to 0. So delta L is plus minus delta L is 2 here. So these tensions are not allowed. So only these two tensions are allowed, and these spectral lines are collectively called as K beta lines. And out of these, this one is K beta 1 and this one is K beta 2. So like this, in our question, it is given the L beta line of X-rays emitted from an atom with principal quantum number 1, 2, 3 arises from the transition of. So if you see here, these are K series, all these are K series. Similarly, if the transition is occurring from M to L, any level, this will be called as L series. And again, if the N to L, then this will be also L series. So all these two transitions are of L series, but like here K alpha, K beta, alpha corresponds to 2 to 1, beta corresponds to 3 to 1. Similarly, in case of L alpha will be corresponding to transition from M to L, and L beta will correspond to transition from N to L. So L is 2, it is 3 to 2, it is 4 to 2. So the transition here occurring, the L beta line, which will be arising from the transition between which two levels, it is n equal to 4 to n equal to 2. So this is the transition from n equal to 4 to n equal to 2. If you consider about transition from n equal to 4 to n equal to 3, then it will be jk klm. This will be m alpha. This transition is L beta. Then n equal to 3 to n equal to 2 we just discussed here. N equal to 3 to n equal to 2 is nothing but k L alpha. This is L alpha. Then n equal to 3 to n equal to 1. N equal to 3 to n equal to 1 is k beta. So these are the transitions and their notations. I hope this is clear to all of you. So Ashwini, is this clear to you? As I can see, you are the only one present here. Can you hear me? Hello, Ashwini, can you hear me? Okay, so let me explain it once again. So here the question says, which transition will be corresponding to L beta lines of X-rays? So if you see, if the transition occurs from L n equal to 2 to n equal to 1, then this is called as K alpha. If the transition occurs from 3 to 1, this is called as beta. Similarly, for L, the transition occurring from 3 to 2, this will be called as L alpha. There is a transition occurring from 4 to 2, this will be called as L beta. So the correct option will be n equal to 4 to n equal to 2, that is option B. Then next question. The question says, find the wrong statement. Option A, energy of characteristics X-ray spectra is very high in compared to ordinary optical spectra. Option B, frequency of characteristics X-ray spectra is very high in compared to ordinary optical spectra. Speed of characteristics X-ray spectra is in free space is very high in compared to ordinary optical spectra. Wavelength of X-ray spectra is very low in compared to ordinary optical spectra. So since in this question, all the comparisons of X-ray spectra is done or are being done with corresponding to optical spectra. So now let's first determine what are the energy, frequency, and wavelength of the optical spectral lines. So if you talk about optical spectra, so this is now optical spectra. So optical spectra corresponds to which wavelength, which frequency. We know optical spectra is the visible spectra. Then if you see in electromagnetic radiation, this is the whole band and this is lambda. Lambda is increasing here, lambda is decreasing here. So the optical spectra corresponds to 400 nanometer to 700 nanometer. So this is the optical spectra region, and inside this optical spectra we have different spectral lines starting from, suppose this is increasing lambda, then lowest wavelength will be of violet, then indigo, blue, GYOR, like this. So red has maximum wavelength, this has maximum frequency. This is maximum lambda, this is maximum nu. So this is the optical spectra. And then the spectral lines at larger value of lambda is called as infrared, and smaller value of lambda is called as UV. Then if you see X-ray spectra, if you consider X-ray spectra similarly corresponds to the wavelength region. If you talk about X-ray spectras, the wavelength region, the wavelength ranges from 0.01 nanometer to 10 nanometer, and the frequency corresponds to 10 to the power 16 to 10 to the power 19 hertz. Or if you calculate exactly, because we know frequency is equals to velocity by wavelength. So if you calculate lambda corresponds to nu, then you will find it as 30 petahertz. Then it is 30 exahertz. So these are the values of frequency and wavelength. So if you see, if the frequency is high, energy E is equals to h nu. So E is directly proportional to nu. So since frequency is high, energy will be high. Since frequency is high, energy will be high. So if you consider the four options, the option says energy of characteristics X-ray spectra is very high in compared to ordinary optical spectra. Now this option is true because the frequency of X-ray spectra are very high in comparison to optical spectra. So we can say the energy is also very high. So the second option is again related to frequency. So it is also very high. So this option is again true. Then the speed of characteristics X-ray spectra in free space is very high in comparison to ordinary optical spectra. Now if you consider all the spectral line, all the parts of this electromagnetic spectrum, whether it be optical, X-rays, microwave, infrared, and all these waves, all have same velocity. That is the velocity of electromagnetic radiation, that is light, which is 3 into 10 to the power 8 meter per second, which is C. So this value is constant for all the regions. So only the constant is this much. So if you see this relation, C is constant and these two vary. If the frequency increases, then the wavelength of the spectrum will decrease. So here this option is wrong because the speed of the characteristic X-ray spectra in free space will be equal to the ordinary optical spectra. But here the option is very high, so it will not be high. The velocities of both, either it's X-ray or it is optical spectra, both will be same. And again, if consider about the wavelength, we have already discussed the wavelength of X-ray spectra is very low because for optical spectra, the wavelength lies between 400 to 700 nanometers, but for X-rays, the wavelength ranges from 0.01 nanometer to approximately 10 nanometers. So this option is again true. So the correct option will be option C, because this option is wrong and we need to find out the wrong statement. So the option C will be the correct option. Then question number 3, the wavelength of X-ray, the wavelength of a X-ray radiation is 4 angstrom. Its energy in electron volt will be, options are option A 12,400 in all these are electron volts, 6,200 electron volt, 3,100 electron volt, and option D is none of these. So I'll give you a few minutes to try this question, then after sometimes I will discuss. So if we discuss, now the question says the wavelength of a X-ray radiation is 4 angstrom, then its energy in electron volt will be. Now similar types of question we have discussed in the previous sessions also. So if you see simple, we know E is equals to h nu or hc by lambda. So if you put the values of h and c, then convert it to electron, it convert energy into electron volt, then the relation will be coming out E. If E is considered electron volt, it will be 1240 divided by lambda, where lambda is in nanometer. But in the question we have the wavelength is given by 4 angstrom. So if you convert this formula to angstrom, it will be energy in EV will be 12,400 divided by lambda, where lambda is in angstrom. So these are the two formulas, and using these formulas, you can easily calculate what will be the value of the energy. So energy in electron volt will be 12,400 divided by, it is 4 angstrom. So if you calculate, it will be coming out 3,100 electron volts. So This is the correct option. Option C is the correct option. The wavelength of an X-ray, if the wavelength of the X-ray radiation is 4 angstrom, then the energy of the electron will be 3100 electron volt, because this is the direct formula. We have already talked about it. It is 12,400 divided by lambda. Then question number 4. The value of Lambda G factor for the level 3D3 is. So here if you see 3D3 means the level is 3D3. So from this, if you compare it to the spectroscopic notation, it is 2s plus 1 Lj. So 2s plus 1 is 3, L is D, J 3. So these are the informations, and the options are A 3 by 2, B 2 by 3, C 4 by 3, and D 5 by 3. So these are the 4 options. I will give you a few minutes to try this question. Then after some time we will discuss. First we will discuss what are the factors which on which the Landau factor value depends, and how the Landau factor value is calculated. We will try to mm, see how we can calculate the Landau factor formula. Then we put these values corresponding to the level given 3D3. Then we will calculate what will be the value of this Landau factor. So let's try it. Then we will discuss. So if we solve this question, now the question says the value of Landau G factor for the level 3D3 is. The options are option A 3 by 2, option B 2 by 3, option C 4 by 3, and option D 5 by 3. So now let's calculate the expression for Landau G factor, then we will put the values. So now if you talk about the Landau G factor expression, we know these G values come in case of the magnetic moment expressions. So now let's see what will be the total magnetic moment expression, because Landau G factor corresponds to the total magnetic dipole moment. So we will take the help of orbital magnetic dipole moment and spin magnetic dipole moment. So we know if you talk about orbital magnetic dipole moment, mu L equal to GL uh, so GL L mu B, where L is L into L plus 1 root over mu B is equals to EH cross by 2m, which is Bohr magneton. Similarly, mu S is GS S mu B. Here if you see GL is 1, but here GS is 2, and mu B similarly is Bohr magneton. So now if you talk about mu J, then mu J will not be directly equal to mu L plus mu S. It will be the component of mu L, since it is mu J, that is total magnetic dipole moment. It will be component of mu L along J vector plus component of mu S along J vector. So if we consider these components, then it will come it will come to the fact that we need to find out the angle between L and J here, and here the angle between S vector and J vector. So if you put these values, we know J vector is equal to L vector plus S vector. So we will use this formula and put all the values, and we will calculate the expression for Gj. So if you see, calculate the expression for Gj will be J into J plus 1 plus L into L plus 1 minus S into S plus 1 divided by 2 J into J plus 1 2 J into J plus 1 root over plus J into J plus 1 plus L plus S into S plus 1 minus L into L plus 1 divided by 2 J into J plus 1 root over. But here if you see, this is G this is mu L term, so GL is 1. But here this is mu S term, GS is 2. So here these two will get cancelled out, and we will get only J into J plus 1. But we know mu J will be written as Gj Mj. This is mu and J vector. Then J vector is nothing but J into J plus 1. So in order to have a J into J plus 1 term here, so if you multiply here by, so this is root over of J into J plus 1. So if you multiply here root over of J into J plus 1, then it will be, the denominator will be J into J plus 1 root over square, then the root over will be going out. So if you add these two after taking the multiplications, Gj will be 1 plus J into J plus 1, because here you see J and here 2J. So this 2J will be getting cancelled out. Then it will be 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2 J into J plus 1. So this is the value for Landé G factor. This is Landé G factor. Now let's come to the question. The question says, what will be the value of Landé G factor for the level 3D3? So now if you see for these levels, what are the values of S, L and J? So from this we can get the value of S is 1, the value of J is 3, and for L the value of for D is D or SPD. So D for D L is 2. So if you put all these values, then what will be the value for? Wait a minute, let me add another slide for it. Or let me let me remove it. Then we will directly put the values here. So now the value of GJ is 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by J into, we just calculated here, 2J into J plus 1. 2, sorry, where was so here it is 2J into J plus 1. And the values of here, since it is D, L is 2, S is 1, and J is how much? J is 3. So these are the values and we will calculate. So it will be 1 plus J is 3. So 3 into 4 plus S is 1. 1 into 2 minus L is 2. 2 into 3 divided by 2 into J is 3. 2 into 3 into 4. It is 1 plus 12 plus 2 minus 6 divided by 24. It is 1 plus 12 plus 2 is 14. 14 minus 6. 14 minus 6, 8. So it is 8 by 24. It is 1 plus 1 by 3, which will be 4 by 3. So the correct option will be option C, 4 by 3. So this is the value of Landé G factor for the level 3D3. So is this clear to you? Yes, Madhikunta Balarajan, is this clear to you? Hello, can you hear me? Hello, can you hear me? Okay, so let me explain it once again. So here is in this question, we need to find the value of Landé G factor for the level 3D3. Now, what is Landé G factor? Like in case of dipole moment expressions, mu L is GL L mu B, mu S is GS S mu B. Then in case of total magnetic dipole moment, mu J is GJ J then mu B. So from this Landé G factor can be calculated. So what will be the value of Landé G factor? It will be the component of mu L along J vector and the component of mu S along J vector. So if you calculate the component of mu L and mu S along J vector, then there will be the angle between J vector and L vector. Again, angle between S vector and J vector. So if you consider this about these angles, so we can use this formula J vector is equal to L vector plus S vector. So j square will be L vector dot S vector into L vector plus S vector dot L vector plus S vector. Then it will be again coming to L square plus S square plus 2LS into the angle between L and S. Like this, we can calculate the angle between L and J and S and J. So if you put these values, we can get the expression. The expression for Landé G factor is 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2 J into J plus 1. If you put these values for the level 3D3, for the level 3D3, L equals to 2, S equals to 1 and J equals to 3. So if you put these values and calculate, the value of the Landé G factor will be coming out 4 by 3. Then question number 5. The question says, determine the normal G-man effect of the cadmium red line of 6438 angstrom when the atom is placed in magnetic field of 0.04 Tesla. The options are 2.2 2.025 into 10 to the power minus 5 angstrom. Option B is 5.05 into 10 to the power minus 4 angstrom. Option C is 4.078 into 10 to the power minus 3 angstrom. Option D is 7.822 into 10 to the power minus 3 angstrom. So we need to calculate the change in wavelength due to the effect of magnetic field, which is the G-man effect. And the strength of the magnetic field is given. It is 0.04 Tesla. And the line which is splitting, the wavelength of the cadmium red line is 6438 angstrom. So I'll give you a few minutes to try this question. Then we will discuss how to calculate the change in the wavelength due to G-man effect. We will discuss a few things about G-man effect, normal G-man effects and anomalous G-man effects. Then we will calculate and try to find out the answer of this question. So let's solve this question. The question says, determine the normal G-man effect of the cadmium rail line of 6438 angstrom when the atom is placed in a magnetic field of 0.04 Tesla. So what is G-man effect? The G-man effect is the splitting of spectral line in presence of a external magnetic field. So we have already discussed in case in vector atom model that the electron which is revolving around the nucleus in an atom acts as a magnetic dipole and it has dipole moment. And when this magnetic dipole or the electron, when it will be placed in a magnetic field, then it will the magnetic dipole moment of the electron motion will interact with the external magnetic field, and due to which there will be the change in energy and there will be the splitting of the spectral lines, because the energy levels will be splitting into a number of energy levels, due to which there will be a number of transitions corresponding to a particular energy value. So a single line will be splitted into a number of components. So in case of normal G-man effect, the G-man effect is basically of two types. One is normal G-man effect, another is anomalous G-man effect. In case of normal G-man effect, the spin of the electron is not considered. That is, only the orbital motion is considered, and the energy splitted and the levels which are splitted in terms of different energy corresponds to the value of different L value. And in case of normal G-man effect, in case of normal G-man effect, a single spectral line splitted into three lines. But in case of anomalous G-man effect, a single spectral line splitted into more than three lines. And in case of anomalous Riemann effect, here the spin is zero, but here the spin is not zero. The spin of the electron is considered. As a result, the splitting is into more number of components. So if you consider the interaction between the two components, like the magnetic field and the magnetic orbit, magnetic dipole moment due to the orbital motion of electron or the spin motion of electron, then there will be change in energy, and this change in energy is given in terms of, like if you remember, the change in energy can be accompanied with the change in frequency, and this is called as EB by 4 pi m. So this is the change in frequency. If the energy change, then the frequency will again change. But we know here the question given in terms of wavelength, we know C is equals to lambda into nu, or lambda is equals to C by nu. Then delta lambda will be minus C by, sorry, I did one mistake here. So nu is equals to C by lambda. Then delta nu will be minus C by lambda square into d lambda. So if we calculate the value of del lambda, then it will be delta lambda will be delta nu lambda square divided by C. Here we have the value of C, which is 3 into 10 to the power 8 meter per second. Then we have the value of delta nu, which is EB by 4 pi m. It is EB by 4 pi mc into lambda square. So delta lambda will be E is 1.6 into 10 to the power minus 19 into 0.04, because the strength of the magnetic field is 0.04 Tesla. Then wavelength is 6438 square divided by 4 into 3.142 into mass of the electron 9.1 into 10 to the power minus 31 into the velocity of light, which is 3 into 10 to the power 8. So if you calculate all these, the value will be coming out. So the value will come out to be 7.822 into 10 to the power minus 13 meter. So it will be 7.822 into 10 to the power minus 3 Armstrong, because 1 Armstrong is 10 to the power minus 10 meters. So the correct option is option D, 7.822 into 10 to the power minus 3 Armstrong. So here in the question it was given that determine the normal Zeeman effect, that is the splitting of the spectral line, that is the change in wavelength of the cadmium red line of 6438 Armstrong when the atom is placed in the magnetic field of 0.04 Tesla. So when the atom is placed in a magnetic field, then there is a splitting of spectral line, and this effect is called as Zeeman effect. The Zeeman effect is of two types. One is normal Zeeman effect, another is anomalous Zeeman effect. In case of normal Zeeman effect, so why this Zeeman effect appears? We know when the electron orbits or moves in a orbital around the nucleus, then due to its motion, it acts as a magnetic dipole, and the magnetic dipole, corresponding to the magnetic dipole, we have magnetic dipole moment. So we have orbital magnetic dipole moment corresponding to orbital motion, and spin magnetic dipole moment corresponding to spin motion of the electron. And we have also the quantum numbers associated with it. So if you see, it has dipole moment, and if we place the atom or the dipole in an external magnetic field, then there will be a magnetic interaction energy, and that will depend upon B vector dot mu vector. Then if you if you talk about the change in energy, and due to this interaction there is the change in energy, and this change in energy accompanied by the change in frequency and change in wavelength. Now the change in frequency is given by the formula Eb by 4 pi m. So we know in the question, but here in the question the uh, known quantity wavelength, which is 6438 Armstrong. So if you convert the frequency into wavelength, then the frequency will be velocity by wavelength. The velocity is, for the spectral line, the velocity is velocity of light, that is c, and the change in frequency is del nu is equal to minus c by lambda square d lambda. So if you put the values, then this del lambda will be del nu lambda square by c, and we know del nu is Eb by 4 pi m. So the value of change in wavelength will be Eb by 4 pi mc into lambda square, and the all are constants, and we know the value of lambda, so we can easily calculate the change in lambda. So the change in lambda will be delta lambda is equals to E is 1.6 10 to the power minus 19 coulomb into the strength of the magnetic field is 0.04 Tesla. Lambda is 6438 into 10 to the power 6438 Armstrong. Then 4 into pi is 3.142. Mass of the electron is 9.1 10 to the power minus 31 kg. Then 3 into 10 to the power 8. So about here will be another term which will be 10 to the power 20, because here the into the minus 20 square of this Armstrong. So if you calculate all this, it will be coming out 7.822 into 10 to the power minus 13 meter, or since 1 Armstrong is 10 to the minus 10 meters, so it will be 7.822 into 10 to the power minus 3 Armstrong. So the correct option will be option D, 7.822 into 10 to the power minus 3 Armstrong. So due to the magnetic field strength of 0.04 Tesla, the splitting of line or the shifting of the line corresponding to wavelength 6438 Armstrong is 7.822 into 10 to the power minus 3 Armstrong. Then question 6, how many electrons will be required to completely fill the 4f subshell of an atom? Options are option A 6, option B 9, option C 12, and option D 14. So these are the options. I'll give you a few minutes to try, then after some time we will discuss. Yes, so question says how many electrons will be required to completely fill the 4f subshell of an atom? So 4f 4f subshell corresponds to n equals to 4 and f equals to f means l equals to 3. S P D F S L is 0, P L is 1, D L is 2, and F L is 3. Now for a subshell having values L, then it has 2L plus 1 number of, for a subshell it has 2N plus 1, 2L plus 1 number of suborbitals. Then for L equal to 3, 2L plus 1 will be 3 into 2 plus 1, it is 7. So 4f has 7 suborbitals. So the 7 suborbitals can be drawn 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So these are the 7 levels. So if you see here, for all these, the value of n is how much? The value of n is, because it corresponds to 4f, the value of n is 4. and the value of L is how much? 3. So value N and L are same. But if you consider about the third quantum number, which is ML, because we know we have four quantum numbers, N, L, ML, and MS. These are the four quantum numbers. So we know corresponding to L equal to 3, we have ML values, and ML has also 2L plus 1 values. So ML will be plus minus 3, plus minus 2, plus minus 1, and 0. So it will be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So these are the labels. And again, in each label, we have MS values plus minus half. That is plus half and minus half. Plus half corresponds to a spin up and minus half corresponds to spin down. So here it will be plus half minus half, then plus half minus half, plus half minus half. So in each subcell there will be two electrons, because according to Pauli's exclusion principle, no two electrons in an atom can have all the four quantum numbers same. So if you see here for all the electrons, N and L are same, but ML and MS are different. So if you list the quantum numbers for first electron, N will be 4, L will be 3, Mn will be minus 3, Ms will be plus half. Then second, 4, 3, minus 3, minus half. Third, 4, 3, minus 2, plus half. Fourth, 4, 3, minus 2, minus half. 5, 4, 3, minus 1, plus half. 6, 4, 3, minus 1, minus half. Like this, 4, 3 will be same for all the electrons. Similarly, we will be having uh, 0 plus minus half, two numbers, 1 plus minus half, another two numbers, 2 plus minus half, another two number, and 3 plus minus half, another two numbers. So these are 6, these are 8. So total will be 14 electrons. So the number of electrons which are required to completely fill the 4f subcell of an atom is 14. So these are the this is the correct option, and the possible or the quantum numbers of 14 electrons are these. The quantum number N and L is same for all the 14 electrons, but the value of ML and MS varies. Then question number 7, the question says an atomic cell with N equal to 2 can contain more than dash number of electrons. Options are option A 4, option B 6, option C 8, and option D 10. So these are the four options. N equals to 2 can't contain more than dash number of electrons. So since N equal to 2, we have to consider all the labels which corresponds to N equal to 2. So I will give you a few minutes, then we will solve how many number of electrons the N equal to 2 label can accommodate. In the previous question, we are only considering about the 4f level, which was corresponding to n equal to 4 and l equal to 3. But since here n equal to 2 is given, so n equal to 2 will contain more than one suborbitals or more than one subcells, not suborbitals, subcells. So we need to consider each subcell. Then corresponding to the subcell, we have suborbitals. Then we will find out the total number of electron which can be accumulated in a n equal to 2 level. So the atomic cell with n equal to 2 can contain more than dash number of electrons. We know for a particular value of n, we can have more than one L values because the value of L corresponds to 0, 1, 2 up to n minus 1. So if you consider n equal to 5, the value of L are 0, 1, 2, 3, 4. That is 5 L values. Similarly, here in question we have n equal to 2. So L will be having two values and those values are 0 and 1. Now corresponds to n equal to 2 and L equal to 0. We have 2s, then corresponds to n equal to 2 and L equal to 1. We have 2p. So these are the two levels, 2s and 2p. So now if you see for 2s, the multiplicity or the number of cell is 1. So 1 because L is 0, number of cell is 12 plus 1, which is 1 for L equal to 0, for L equal to 1, 12 plus 1 is 3. So 2s has one cell, but 2p has 3 subcells. Then 1, 2, 3. Then if you consider for this L equals to 0, but for this L equal to 1, so ML will be plus minus 1, 0, plus 1, minus 1, and 0. So 1 corresponds to plus 1, another 0, another minus 1. These are the ML values. Then MS is similarly plus minus half for all cases. So you have 2 electrons here, then 2 electrons here, 2 here, and 2 here. So this is 2 corresponds to 2s and 6 electrons corresponds to 2p. The total will be 8 electrons. So the correct option is option C, that is 8 electrons. Now let's consider about the quantum numbers of the electrons. So if you see what will be the quantum number of those electrons, the quantum number of those electrons will be suppose n, l, ml, ms. So for 2s there are 2 electrons. So L is 0, N2, L is 0, ML is 0, S is plus minus half. It has 2 electrons. Then for 2p, N is 2, L is plus 1, 0, minus 1. Sorry, L is 1, ML is plus 1, 0, minus 1. So MS is plus minus half, plus minus half, plus minus half. So it is 2, 2, and 2. Total 8 electrons. So for one side it is 200 plus half, 200 minus half, then 211 plus half, 211 minus half, 210 plus half, 210 minus half, 21 minus 1 plus half, 21 minus 1 minus half. So these are the 8 electrons and the quantum numbers of these 8 electrons. So the total number of electrons. Similarly, if the question said for n equal to 8 level, what will be the maximum number of electrons? It will be the multiplication, it is the summation of the sum of all the labels it contains. So it will count L equal to 0, 1, 2, 3, 4, 5, 6, 7 like that. So you to add all the number of electrons that each orbital contains, because each orbital is again divided into number of suborbitals, so you will need to calculate. Then question 8, the question says the hyperfine splitting of the spectral line of an atom is due to A, the effect of external magnetic field, B, the coupling between electron spin and nuclear spin, option C, coupling between spin and orbital angular momentum of the electron, and option D, the coupling between two or more electrons. So if we consider the question says the hyperfine splitting of the spectral line of an atom is due to the effect of external magnetic field, the coupling between electron spin and nuclear spin, the coupling between spin and orbital angular momentum of the electron, the coupling between two or more electrons. So now let's discuss each option in a detailed way. So if you see the question says hyperfine splitting. So there are different types of splitting. We have studied about fine structure splitting. We have studied about G-man splitting. We have studied about stack splitting. We have studied about um, spin orbit splitting. So there are different types of splitting. Now one is hyperfine. The question says hyperfine. We have fine structure splitting. So fine structure splitting corresponds to the interaction between electrons spin angular momentum and electrons orbital angular momentum. That is, spin angular momentum is S vector and orbital angular momentum is L vector. So due to these two interactions, we get fine structure. That is, the transition from n equal to 2 to n equal to 1. There was only one transition. Like if you see, this is n equal to 1, this is n equal to 2. So the transition, there was a single transition, but this one level, if you consider about spin orbit splitting, then this is converted to 1s half, then this is splitted to 2s half and 2p half, 2p 3 by 2. So here there are, so the n equal to 2 level again splitted into 3 levels. So the transition will be now, this is one level, this is 3 level. The transition will be from 2p half to 2p half to 2s half, 2p 3 by 2 to 1. So there are two transition. So this one transition, which was normal spectra or hydrogen spectra, which was according to the no, normal models, which was given by Bohr Sommerfeld. But if you talk about the spin orbit splitting, due to the spin orbit interaction, we have this Lj, and due to this Lj, we have the total quantum number Lsj. Total quantum number is J. J vector is L vector plus S vector. Then we got one line is being split into two lines. Similarly, we know when the atom is placed in an external magnetic field, then the splitting is called as G-man splitting. So the first option is the splitting of the effect of external magnetic field is called as G-man splitting. So this is not the correct option. The coupling between electron spin and nuclear spin. So this is the correct option. So I will come back to it later. Now let's consider about the fine structure. So fine structure is the splitting between the coupling between orbital and spin angular momentum of the electron, which is fine structure splitting, which is J vector corresponds to L vector plus S vector, and this is fine structure splitting. Now fine structure splitting also corresponds to JJ coupling and LS coupling. So there are two couplings. So one is LS, another is JJ. So in case of LS, what happens if there are more number of electrons, because only hydrogen has one electron, but there are many atoms which are many electron system. So if there are two or more electrons, then it depends upon the atom, like whether the atom is small or atom is large. That is, it depends upon the Z value, whether there will be LS coupling or JJ coupling. Basically, LS coupling is written as capital L and capital S, but JJ coupling is written as small j and small j. So here, since it is small L and capital L and capital S, so it shows that this L corresponds to total orbital quantum number, that is L1 plus L2 of a number of electrons. S corresponds to S1 plus S2 of a number of electrons. So this is the fact between, this is the concept underlying the LS coupling. But in case of JJ coupling of a single electron, the coupling occurs first. There is coupling between the spin and orbital angular momentum, that is J small j is equal to small l plus small s. So this is orbital and this is spin. So this coupling between spin and orbital angular momentum, we can specifically say as it is JJ coupling. but the coupling between two or more electrons can be called as LS coupling. Now, the correct option is option B, which is the coupling between electron spin and nuclear spin. So there what happens? We have J is equals to L vector plus S vector, but in case of hypersplice splitting, F vector is equal to J vector plus I vector. So this J vector is electron spin and the I vector is nuclear spin. So the total angular momentum is F vector, which is called as total, which corresponds to electron spin plus nuclear spin. So the interaction between the spin of electron and the spin of nucleus results in hyperfine splitting. The correct option is option B. Then question 9. X-rays are produced using cobalt Z equal to 27 target. It is observed that the X-ray spectra contains strong K alpha line of wavelength 1.785 Armstrong and a weak K alpha line of wavelength 1.93 Armstrong. The weak K alpha line is due to an impurity whose atomic number is. So this is a very good question. Also, it is mentioned that we have to consider that the skinning effect is same for the both and the screening effect is 1. So we will solve the question, and the options are option A 24, option B 25, option C 26 and option D 28. So if it is pure cobalt, that is Z equal 27, then we will be having a strong component of K alpha which corresponds to 1.785. But since there is some impurity, the K alpha line corresponds to the another K alpha line which is very weak or low in intensity, and this line corresponds to a wavelength of 1.93 Armstrong. So we have to find the wavelength of 1.93 Armstrong corresponds to which value of Z. So that will be the atomic number of the impurity. So this is a very good question. So I will uh, uh, let you to try it for some. I will give you a few minutes to try it. Then after some time we will discuss in detail how we will approach this problem. So the question says, if the the strong K alpha line, and the wavelength it corresponds to is 1.785 angstrom, and the weak K alpha line corresponds to wavelength 1.93 angstrom. So if the sample is pure, then only 1.785 angstrom line will be coming, but since the impurity is present, so the impurity corresponds to 1.93 angstrom. So now also we have to consider the screening effect is same for both the cases. So according to Moseley's law, if you see it is K alpha line, the K alpha line corresponds to transition from L equals to n equals to 2 to n equals to 1. So if you talk about the change in energy, then delta E will be, which is equal to S nu, is RHC. Then considering the screening effect, there will be J minus 1, because here it is screening effect is same for both and it is 1. So J minus 1 square divided by 1 minus J minus 1 square divided by 2 square. It is 1 square, it is 2 square. Like in case of hydrogen atom, we are taking the torn value, so it is more or less like this only. So if you see, this is then the wave number is C, which is R. So this is the wave number. We will calculate the wave number, then we will calculate the wave number, then we will calculate the value of the Z. So now you see, and this is wave number nu bar. So nu bar will be frequency by velocity. It will be R Z minus 1 square minus Z minus 1 square by 4. So if you calculate, then 1 by lambda will be 3R by 4 Z minus 1 square. So this is the general formula. So here 1.785 corresponds to Z equal 27. So 1 by 1.785 corresponds to 3R by 4, 27 minus 1 square. Similarly, we need to find out 1 by lambda impurity will be 1 by this is 1.93 angstrom. So 1 by 1.93 is equal to 3R by 4 Z minus 1 square. So from this, from the first, we can take the value of R. Then if you take the value of R, we can put it to get the value of Z here. So if you put this, the value we will be getting. So we can simply say, or you can, since 3R by 4 is same for both, we can directly write. So 1 by lambda impurity. So lambda impurity divided by lambda cobalt is equals to 27 minus 1 square divided by Z minus 1 square. If you see, it will be Z minus 1 square will be lambda cobalt by lambda impurity into 26 square. So if you calculate the values, then it will be, one is 1.785. So 1.785 divided by 1.93, 1.93. This is 0.92 root over. So this is 0.92 into 26 square. So if you calculate, Z minus 1 will be 0.93 into 26 square square root, which will give you Z equal to Z minus 1 equals to 25, Z equal to 25 plus 1, 26. So if you see 0.93, the root of 0.93 is how much? So square root of 0.96. So it will be coming out Z 26. So this is the value. So Z equal to 26 is the correct option, option C. So here if you see, the question says the X-rays are produced using cobalt Z equal to 27 target. It is observed that the X-ray spectra contains strong K alpha line equivalent to 1.785 angstrom and a weak K alpha line corresponds to 1.93 angstrom. The weak K alpha line is due to an impurity whose atomic number is, you have to calculate. And consider that the skinning effect is same for both, which is 1. If you see the transition of K alpha corresponds to n equal to 2 to n equal to 1. So the according to Moseley's law, considering the torn values like in hydrogen atom, we can say the change in energy is RHC Z minus 1 square by 1 square minus Z minus 1 square by 2 square. So if you calculate 1 by lambda will be 3R by 4 Z minus 1 square. So 3R by 4 gets cancelled for each. Then if you take the ratio, then lambda impurity by lambda cobalt will be Z minus 1 square by Z minus 1 square. So one Z is known, that is cobalt 27. Another Z is another Z we need to calculate. So if you calculate, the value will be, the Z minus 1 will be 25 or Z will be 25 plus 1, that is 26. So this is the, so option C is the correct option. That is the impurity is Z equal to 26. Then question number 10. The question says an atom is in 3D 3 state. The angle between orbital and spin angular momentum vectors, that is L vector and Ls vector, is A is cos inverse root 3 by 2, cos inverse 1 by root 3, cos inverse minus 1 by root 2, and cos inverse 1 by 2. So I'll give you a few minutes to try, then I will solve it. So if we solve, we know J vector is equal to L vector plus S vector. So J square will be L square plus S square plus 2 LS cos L vector dot S vector. So cos L vector S vector will be J square minus L square minus S square divided by 2 LS. And we know J is J into J plus 1 root over, L is L into L plus 1 root over, S is S into S plus 1 root over. So these are the values. So if we put here, cos L vector S vector will be J square. J square is nothing but J into J plus 1 minus L into L plus 1 minus S into S plus 1 divided by 2 LS L into L plus 1 root over S into S plus 1 root over. Now, this is 3D3. For 3D3, we have S equal to 1, L equal to 2, J equal to 3. S equals to 1, L equal to 2, J equal to 3. So if you put the values, it will be 3 into 4 minus 2 into 3 minus 1 into 2 divided by 2 into root 6 into root 2. So it will be uh, 12 minus 6 minus 2 divided by 2 into root 12. It will be 12 minus 8 is 4. 4 divided by 2 root 3. 4 divided by uh, 4 root 3. 2 is outside already. 4 root 3. This is 1 by root 3. So it will be cos inverse 1 by root 3. So this is the correct option. Option C, option B, cos inverse 1 by root 3 is the correct option. That is the angle between orbital and spin angular momentum vectors for 3D 3 state. Then question 11. The L, S, and J quantum numbers corresponding to the ground state of electronic configuration of boron are option A are L equal to 0, S equal to half, J equal to 3 by 2. Option B, L equal to 0, S equal to 0, J is equal to 3 by 2. Option C, L equal to 1, S equal to 3 by 2, J equal to 3 by 2. And option D, L equal to 1, S equal to half, J equals to half. So I'll give you 1 or 2 minutes to try it, then I will discuss. So question says the quantum numbers correspond to ground state electron configuration of boron. Now boron corresponds to Z equal to 5. So 1s, 2s, 2p, 1s2, 2s2, 2p1. So it has 2 electrons, it has 2 electrons, 2p has 1 electron. Now corresponds to p, we have px, py, pz, that is 1, 2, 3. Here only one is here, minus 1, 0, 1. This is the ml value. Then this plus half minus half, s value. So s is half. For 1 electron, s is half. For 1 electron, s is half. For p, l is half. So considering the spin orbit splitting, j is equal to l plus s and l minus s. So half plus minus half. So it will be either 0. 1 minute. L is not half. L is 1. Because it is P, for P, L equals 1, it will be L plus S, that is half, 1 plus half or 1 minus half. 1 plus half is 3 by 2, 1 minus half is half. So J value is 3 by 2 and half. S is half, L is 1. And we know the spectroscopy term is 2s plus 1 Lj. S is half, so it will be 2s plus 1 will be 2. So it will be 2p half and 2p 3 by 2. So these are the two levels, but it is even that is the ground state configuration, because if you see 2p half and 2p 3 by 2, L equal to 1, S equal to 1, J equal to half, L equal to 1, S equal to. So these are the four options. But if you see, the question says ground state electronic configuration. So ground state, whether the ground state will be 2p half or the ground state will be 2p 3 by 2. Here there are some rules which are taken into consideration before deciding the ground state. It will be studying in more details in the spin orbit coupling term like many electron atom discussion, but you can just remember that if the cell is less than half filled, then the J value, the lowest J value, that is the L minus S, corresponds to the ground state. And if the orbit is more than half filled, then the highest J value corresponds to the ground state. So here, if you see, P can have 6 electrons, but here P has 1 electron, so it is less than half filled. So less than half filled means the value of J will be L minus S, that is 1 minus half, that will be half. So the ground state corresponds to J equal to half, and the ground state is 2p half. So for 2p half, L equal to 1, S equal to half, and J equal to half. So the correct option will be option D. Now, let me explain it once again. So here the question says we have to find out the quantum numbers for the ground state of electronic configuration of boron. For boron, boron has 5 electrons. So corresponding to Abba's principle, it is 1s, 2s, 2p, 3s, 3p like this. 1s will be having 2 electrons, 2s will be having 2 electrons, and 2p will be having the remaining 1 electron. So the remaining 1 electron, it is in 2p. So for p, L equal to 1, and for 1 electron, S is equal to half. So here considering J, J will be plus minus L plus minus S. So 1 plus minus half, 1 plus half is 3 by 2, 1 minus half is half. So the levels are 2p half and 2p 3 by 2. But out of these two, what will be the, or which one will be the ground state? Because if you consider the Hund's rule, according to this rule, if an orbital is less than half filled, then the ground state corresponds to the lowest J value. If the orbital is more than half filled, the ground state corresponds to the hash J value. So since it is less than half filled, the ground state will be L, J is equal to L minus half, which is 1 minus half, that is half. So the ground state is 2p half. And if you consider 2p half and compare it to the 2s plus 1 L by J spectroscopic notation, we will found S is equal to half, L is equals to 1, and J is equal to 1. So the correct option is option D, and all the other options are incorrect. So these are the questions I wanted to discuss with you today. So in the next class, we will be solving a few more problems, which will be based on the week 6 lectures. Now that's it for today. Good night.